about energy, but let's talk a little bit more specifically about the different kinds of energy that we encounter in everyday life and define them a little more specifically. So one type of energy that we are going to definitely use in this class is kinetic energy, and that's denoted with a capital K. Kinetic energy is the energy of motion. If you remember, the word kinetic actually means to move, and we talked about it in kinematics. So the energy of this wrecking ball when it runs into a building is actually transferred into the building and causes it to be destroyed. Another type of energy which we're definitely going to talk about is the gravitational potential energy. This is the energy associated with an object's height. So for instance, at the top of the arch of this roller coaster has a lot of potential energy due to the fact that it's so high. That potential energy will actually get converted into kinetic energy as it slides down and goes faster at the bottom of the roller coaster track. Another type of energy that we'll talk about, and you may have already seen in some of your labs, is elastic or spring potential energy. This is the energy associated with stretching an object. So for instance, in this bow and arrow, you can see that the string of the bow is being pulled back taut, and that's going to give both the string and then, of course, then it's going to contribute to the arrow's motion or kinetic energy. Another example of a type of energy we're definitely going to talk about in this class is thermal energy. Thermal energy is related to the temperature of a gas, and that's how we're going to talk about it later as the sum of all the molecular, kinetic, and potential energies. We're not going to touch on so much in this class chemical energy or nuclear energy. Chemical energy is the energy stored in molecular bonds, and nuclear energy is the energy stored in nuclear bonds, which is even higher than chemical energy. These can be quite energetic, as you know, because they are the sources of many different types of explosions, but they're mostly dealt with in chemistry class, and we won't talk about them so much here. So let's talk again a little bit about a system and its environment. The total energy in a system can consist of many different forms of energy. So this total energy, if we're looking in just inside the red box here, not talking about the environment at all, can consist of the kinetic energy, the gravitational potential energy, any kind of spring energy that might exist, thermal energy, chemical energy, etc., etc., etc. Again, if we have no interactions with our environment, i.e. the system is closed, then the change in energy of E total is 0. And that means that we can get transfers, though, between the different kinds of energy. So just like we saw in the last system, K can turn into U can turn into K, and you can have all kinds of different things. Let's talk about some more specific examples of energy transformation. In this case, we have a bodybuilder who is lifting a very heavy weight. I guess this person is really a weightlifter, I don't know, in the Olympics, clearly. And they can lift a very heavy weight very high into the air. The height of an object is related to its gravitational potential energy. So obviously, something is being turned into gravitational potential energy. In this case, it's the chemical energy in the person's muscles as they are actually performing the lift. In the example of a baseball player that runs and slides into third base, you can see that the kinetic energy that the baseball player had when he was running is actually being turned into another type of energy. We know about what's happening here, which is that there's a lot of friction between the runner and the ground as he slides into the base. And when there's a lot of friction, you actually end up heating up systems, and that leads to some kind of thermal energy. So because the temperature increases. So this is an example of turning kinetic energy into thermal energy. We can also turn other types of energy into thermal energy. In particular, when you set a fire, you can turn the chemical energy that's bonding the molecules together and you're actually going to cause a chemical transformation of those molecules, and again, releasing heat when you do this. Other types of reactions that are exothermic also release heat. You can also have endothermic reactions which absorb heat. And heat, like work, is a transfer of energy. And If the temperature goes up or down, then you can also change the thermal the thermal energy, which is this E thermal. And finally, here's a very interesting and complicated example of a diver who's going to jump off of a springboard, jump into the air, and then dive into a pool. The springboard has some kind of spring energy, we'll call it U spring, and it's kind of a stored potential energy. That can be turned into a kinetic energy as he is lifted up into the air at a higher velocity. That kinetic energy, though, will turn back into gravitational potential energy as he goes higher and higher into the air, and then eventually at some point he'll reach the maximum height with his maximum gravitational potential energy and begin to fall again, where his velocity will increase because he's accelerating due to gravity. Again, increasing velocity means increasing motion, which is increasing kinetic energy. And so you can see this is a very complicated system where energy from the board is turning into kinetic energy of the person, which is turning into potential energy of the person and back into kinetic energy of the person. Now let's finally talk a little bit about energy conservation. We basically just said the same thing, but let's make it a little bit more concrete. When you have an isolated system, it doesn't interact with its environment. That means the total energy of the system is constant. That's why the change in total energy is zero. Delta E total equals zero. In this case, you can still have energy transformations from one kind of energy to another. Kinetic into potential, potential into chemical, chemical into thermal, but this is all happening within the closed system, so the energy of the entire system is constant. On the other hand, if you have a system that is interacting with its environment, there's still a law of conservation of energy, but you have to now include energy transfers. This is the change of total energy from the non-isolated system. It's equal to the energy transferred into or out of the system as work or as heat. So once again, if we're talking about, losing energy due to friction when the baseball player was sliding into third base, then you can have heat leaving the system, causing the system to overall lose some energy. And that means that energy is being transferred into the environment in the form of heat. The change in the system's energy equals the amount of work done or heat transferred into or out of the system. Delta E equals W plus Q. You've probably seen this in thermodynamics and chemistry class before. We will come back to this concept later on, including heat, and we will kind of use that concept basically from now on in the class. We won't define heat formally until we get to thermodynamics though.